Is recording. Okay, so welcome you all to the CMB Bharat Cosmology seminar series. So it's like a monthly event. So today I'm pleased to introduce our seminar speaker, Dr. Susmita Adhikari from IISER Pune. So she obtained her PhD in astronomy from University of Illinois, Urbana, Champaign. After her PhD, she was a postdoctoral fellow at Kavli Institute of Particle Astrophysics and Cosmology, Stanford University. She then spent a year, a postdoc in joint position between the Department of Astronomy and Astrophysics at the University of Chicago and Fermilab before she moved to IISER Pune. So she studies the formation and structure of dark matter halos and the co-evolution of galaxy within. Her work involves theory and simulations to interpret the observation of gravitationally bound objects ranging from massive galaxy cluster to faint galaxy to learn the underlying nature of dark matter and gravity. So today she will talk about the structure of dark matter halos and their measurements. So over to you.
Okay, yeah. So thank you for organizing this. It's nice to meet the community as well. So I primarily work on these nonlinear structures called dark matter halos and try to understand how we can, what we can learn from the structure of dark matter halos that will better help us understand some of the fundamental questions in cosmology about the nature of dark matter, gravity, and so on. So I'll be talking about some work that I've been doing over the past many or few years in understanding these observations. So just to start off, so just going to the beginning, dark matter halos are essentially, you can think of them as the endpoints of structure formation, right? So they form out of initial peaks in the matter density that essentially gravitationally collapse and form these self-bound virialized structures that are essentially the regions within the potential wells of which the stars, galaxies, and all of our visible universe we think evolves and grows, right? So it's essential in some sense to understand how structure forms to understand our observable universe. So these halos, these final collapsed objects are also they are the densest regions of dark matter in the universe, and therefore their structures are their internal structures are really good laboratories to study how dark matter how dark matter properties essentially affect the distribution of dark matter inside of these objects. So in the standard cold dark matter scenario, where we think that we can, in the most vanilla model, if we think of dark matter as 1 GeV WIMP, 100 GeV WIMP, we can think of halos forming down to almost Earth mass, right? So we have a whole spectrum. So we have hierarchical structure formation where halos form at low mass scales going to large cluster mass scales as well. So in the standard scenario, you would form halos that are Earth mass down to halos that are 10 to the 13 to 10 to the 15 solar masses that appear in the sky as clusters of galaxies. But in many ways, the dark matter halo and the largest objects contain these clusters of galaxies, whereas the smallest, the least massive visible objects, visible halos, we think are the halos of these faint dwarf galaxies. And then even beyond, in the left-hand side of this figure, you can have halos that within which galaxy formation has not happened or has happened long ago, and they're completely dark. In the entire, but through this entire spectrum, of course, it turns out that in the structures of dark matter halos are in some senses very similar. The way in which dark matter clusters inside of the halos of these objects is very similar across various mass scales, or their physics can be understood universally across these mass scales in many ways. Right, so dark matter halos have been studied quite extensively. through through observations, which I will talk about later, and also through simulations. And actually very extensively through simulations. And it was seen particularly when people studied n-body simulations of dark matter, of cold dark matter, that typically over the past 20-ish years, the wisdom has been that these halos, the density inside of these halos, which is shown on the left plot. So these are plots from Aquarius simulations at different resolutions. The y-axis is the density and the x-axis is the distance from the center of the halo. So it turns out that these halos are quite well described by what is known as these NFW profiles, Navarro-Franken-White profiles, where essentially the dark matter reaches an equilibrium state inside of these nonlinear collapsed virialized objects, where the slope of the density profile, which is on the right, approaches sort of the density falls off as -1 in the inner region, and in the outer region just goes as -3. So it appears that these profiles tend to emerge when cold dark matter cold dark matter n-body simulations. So another very intuitive way of looking at dark matter, while these profiles have been studied quite extensively, there was quite the inner profiles are quite well converged. However, in the outer regions of these dark matter halos, in these regions, for example, they received somehow a lot less focus, right? So there was a lot of substructure falling in over there, and understanding the emergence of these outer parts of the dark matter halos was actually is something that has been more clearly developed in the past few years. So one nice way of looking at dark matter halos is also through its phase-space diagram. So one of the questions that has been in the community is, where is the boundary of a dark matter halo, right? So we saw the picture of a dark matter halo earlier. This is the large-scale structure. Each of these nodes is a dark matter halo. But what exactly defines the boundary of this object, right? What exactly defines the influence of this object in some sense? And is there any, so typically people would use something like a standardized density, like a virial over density, where some radius would contain some x times the mean density of the universe, and call that the size of the halo. But if you actually look into the phase-space diagram of a halo is not, you'll realize that a halo, the structure of a halo can be thought of not just as some region containing x times the overdensity of the universe. There is actually a very detailed phase-space structure naturally inside of these objects, which actually carry very important information about how to understand these objects. So if you look at the phase-space diagram, which is where I've, essentially this is from an idealized simulation, the y-axis over here is the velocity with which a particle is falling towards a halo. So it's the radial velocity towards the center of the halo, and the y-axis is the distance from the center of the halo. And in this phase, and if you plotted all the radial velocities of all particles in a halo as a function of in this space, it would appear to follow this structure. So far away from the halo, so as you can see that there are actually very distinct boundaries in the phase-space structure of a dark matter halo. There are very distinct regions. So far away from the center of the halo, you are in a region which is, the particles are simply expanding with the Hubble background. They have not yet turned around. As you move towards the center, you reach a turnaround radius where it's turning around for the first time. So, there's an overdensity at the center, so it cuts off from the Hubble flow and starts to fall in. And then finally, you see this multi-streaming region. So the particle falls towards the center with more and more negative velocities and starts to orbit in the halo potential, forming this multi-streaming region. So essentially, this multi-streaming region is where particles are orbiting. So that's why, and shell crossing is essentially happening. So at one radius, you have many different shells that have different velocities that are crossing each other simply because these dark matter particles are orbiting in these shells, right? So this orbiting bound collapsed nonlinear structure is what we think of as as the virialized structure. Whether the entire halo is virialized or not is a separate question. But essentially, this multi-streaming region is very distinct from this single stream infall region in the halo. And in this phase, there's a very clear boundary to where the dark matter is inside and outside of this multi-streaming region. So this region, this point over here, where particles fall in, then turn around in their orbits, reach the pericenter, then just simply turn around to this point, smoothly crossing the center, and then they go out in the orbit until they turn around inside the halo in their orbit for the first time or reach their apocenter. And this is, this first apocenter of the most recently accreted particle is what forms what is known as the splashback radius. So it's splashing back or reaching apocenter and falling back in again, and forms this boundary of the dark matter halo. Please feel free to stop me and ask questions. Right. So moving on. So even the one that I was showing you earlier was an idealized simulation self-similar collapse of a single power law peak in the universe, spherical collapse of a single power law peak in the universe. If you have more, if you introduce more parameters like putting in shapes, your phase space structure becomes more diffuse. You then don't have just narrow cold streams, you have diffusion just because of the different angular momentum of the particles that have come in, and you start to relax this picture. In the normal, so this phase space picture is related, of course, to the density simply by integrating along the radial velocity direction. If you had idealized halos, you would see actually these caustic features everywhere in your dark matter halos. But because of non-sphericity and many other things in hierarchical formation, you don't actually see these caustics, but this outer boundary still becomes very, very distinct. So you can still see that these E's are of halos of different ellipticity, and you can see that as you move from the outer to the inner region, there's a huge jump in the density profile that corresponds to this jump in phase space density. So essentially, the structure, the region around a halo can be broken up into various parts. One is the orbiting or the multi-streaming region, the Hubble flow, and of course, the infall region where the particles are simply just falling in for the first time. Right. So, so that was, I was showing you an idealized case. This was actually seen even in n-body simulations where you're not just simulating a single peak. You have the whole cosmological evolution of a field of density peaks where objects are merging. The peaks have different shapes. Even there, there the final collapsed halos is not just this collapse of a single spherical peak, but of this entire hierarchical merger scenario. And what was noticed that even in n-body simulations, if you picked halos that are of similar masses, and if you looked at their density profiles, which is in this top panel, while the inner, so this is the top panel is the density, the bottom panel is the slope of the density profile. So R over R, it's plotted as a function of R over R vir, which is R over R virial. And, so typically the size of the halo is somewhere here. And what is seen is that while inside and and if you look at the slope, remember that NFW tells you that the slope should be about -1 in the inner region and -3 in the inner region. So it's this dot dash line. But it was seen that even in simulations, even when you stack over halos of variety of different formation histories, which have similar masses, there's actually a very sharp feature that stands out in its profile. In the outer regions of the halo, the slope of the density, the rate of change of the logarithmic density becomes very, very steep in a nano confined region in the outer parts of the halo. So when we compared this to, sorry, there should be a citation here. This is from Dima Kravtsov. When we I don't know if it's there. Okay. When we compare this to the phase space of n-body simulation halos, so this is the phase space of the n-body simulation halos, so similar VR over the distance from the center. And again, you see this, here this is stacked over many different kinds of objects. So you don't see the beautiful caustic-like features that you were seeing over here. Those get averaged out. But you still see this very large jump between the inner region of orbiting objects where particles have both positive, negative velocities in orbits compared to this infalling region where particles have negative infalling velocities. And this dip in the density occurs exactly where this transition happens. Right? So the density profiles of halos are not simply NFW. They tend to NFW, but actually they cut off. So the inner part of the halos essentially cuts off at some finite radius, which corresponds to the boundary of the halo, or as we call it now, as the splashback radius, right? So that essentially defines what the boundary of a halo is. And you can clearly see that it stands out in the slope profiles. If you look at how the density changes as a function of radius, there's a clear feature in the slope profile. Right, and over time we've understood that this boundary depends very strongly on the accretion rate of the halo. Of course, it depends on the mass of the halo. The larger the halo, the larger the boundary. It also depends on how fast the halo is growing. Because this is a dynamical boundary traced by the most recently accreted particle at its apocenter, between when it falls in and when it reaches apocenter, the halo accretes more mass and it grows. So it can't go as further out if the halo was not accreting mass. So if the halo was not accreting mass, it was just a static thing, the particles would come in and just splash back to the first turnaround radius where it cuts off from Hubble flow. But because the halo is growing, the apocenter, or this boundary, shrinks because of the rate of growth of the halo mass between in the time scale that it takes. So faster accreting halos tend to have a smaller splashback radius compared to slow accreting halos. And not just the splashback radius, as you can see that the inner profiles of halos are also so here gamma is the accretion rate of the halo, which is the mass accretion rate. So how quickly the mass of the halo grows with time over the history of the universe. So as you can see, things which are very slowly growing or slowly accreting tend to have very different. Not only do they tend to have very different splashback radii, they also tend to have very different inner slopes as well. So there's a lot more information inside the halo profile beyond what we think of it as a single virialized object. The advantage of the splashback radius is that we can understand it from very simple physical principles. It's actually very easy to predict where this feature should lie. But in general, the entire profile and the structure of the internal structure of the halo is very sensitive to its growth history. Right. Not only dark matter. So halos, the potential well is formed by dark matter. But as we know, in hierarchical structure formation, not only are diffuse dark matter particles falling into a halo, other smaller halos that, in CDM, small halos form first to merge into larger objects. So not only are diffuse dark matter particles falling into a potential well, if you look at a dark matter halo, which is shown over here, there is a lot of substructures. So there are a lot of smaller halos that fall into larger halos. So their dynamics are also very similar. So each of these smaller halos actually may contain galaxies within them. So essentially, the distribution of galaxies are also in some sense collisionless. The dynamics of galaxies is also collisionless, and they also tend to follow a similar distribution inside of dark matter halos. So, for example, if you looked at the logarithmic slope as a function of radius for dark matter particles, which is this black dashed line, this is from simulation. So this is the black dash line from particles. The colored lines are essentially those that correspond to subhalos or these substructures, and so if you look at the density of substructures as a function of radius in a dark matter halo, they also show this splashback-like feature. In fact, you expect them more or less to be at the same place as the dark matter. But of course, unlike dark matter particles that are orbiting inside a halo, subhalos actually evolve, they're extended objects, so they feel tidal forces, and they also feel dynamical friction. So in particular, because of dynamical friction, if you have a very massive substructure moving through a gas of diffuse dark matter particles, it'll feel dynamical friction and lose some of its energy, and therefore its splashback is shifted inside. But overall, this feature should exist in all collisionless components inside of dark matter, inside of a dark matter halo. It's in some sense, it's if you have a collisionless halo surrounding a galaxy, you should be able to see this feature. So, right. So this physics of understanding many parts of the halo is quite simple. It's gravitational collapse of collisionless dark matter in an expanding universe. You can try to break each of these assumptions. You can try to understand what happens to the internal structure if we change gravity, if we change the way dark matter interacts, if we change the expansion properties of the universe. So I won't go into the details of all of this, but essentially we've over the past few years we've learned that because this boundary of the halo is so easily understood from first physical principles, it's actually very easy to try to predict what happens when you change the different components that tend to set this boundary. So, for example, in modified gravity, I won't go into this. So, if you look at the distribution of galaxies in a cluster mass halos in GR versus say F of R gravity, the distribution of galaxies as a function of mass actually changes quite significantly, particularly because galaxies that are falling into a cluster mass halos or subhalos that are falling into a cluster mass halos feel different amounts of dynamical friction, which changes their location for this outer boundary.
So, Susmita, if I want, so what is the observational situation here? I mean, like you have these distinctions.
Yeah.
How far are we from being able to actually use them for, putting constraints on F of R gravity or
Yeah,
things like that?
we have observations. So I'll be talking about observations.
Okay,
like
great.
about 3-4 minutes. Yes.
Okay, no. Sorry.
Yeah. Yeah, so the observations are actually really, really good. We are, I would say, in some senses, even theory limited. But yeah, we've been working in the observations. Okay, so right, so this is in modified gravity. In self-interacting dark matter, if you look at the same phase space that I was showing, because now self-interacting dark matter is something that I've been working on over the past few years. Dark matter particles have an additional interaction beyond gravity. And it gives them another way of exchanging energy to redistribute energy among themselves. So it really changes the internal structure of halos. And you can also then try to understand how it, you can also try to then go and measure. So this is a CDM halo on top, and this is an SIDM halo on in the bottom, run with a centimeter square per gram cross section. And their internal structures, as you can see, is quite different. Right, so the SIDM halo is much more diffuse because it has been able to redistribute energy, unlike the dark matter where you can actually see CDM, where you can actually see streams, and it also has predictions for the slope or way the matter is distributed inside of these objects. Right. So yeah, and then we've also been looking at changing the equation of state of parameter. As expected, all of these things tend to have an effect on the structure of dark matter halos. And the question is, why is this internal structure of interest? And of course, one of the reasons why the details of these internal structures is interesting is actually because a lot of it is accessible observationally. Apart from getting a clearer understanding of the boundaries of halo, we now understand that it is a very strong probe of the growth history of the halo. It provides a physical definition of halo mass. It's really a fundamental length scale. Like the boundary of the halo is a fundamental length scale in a halo structure. It should be there if there is dark matter. So it's kind of like evidence for dark matter as well. But I think it's most exciting currently to me because it's accessible observationally, right? So a lot of these features we can try and go and see if they're accessible observationally. Right, so I won't go into much of the details of this. So far, halos are sort of thought of as this single, particularly when people are working on large-scale structure, and for justified reason, you think of them as these virialized objects where things have become very nonlinear and you only treat them in an effective way. But actually, these halos are more than just a single virialized object with an NFW profile. They have a lot of internal structure, and their internal structure affects very strongly what we interpret about the large-scale structure, and also galaxy evolution within them, right? So we've also been looking at machine learning to study these internal structures in detail, and we're really seeing that if you take all the particles in a dark matter halo, divide them up into the time at which that part, the particles entered that object, and you can see that there's actually a very strong bimodality or a trimodality. So there's an old part of the halo which is virialized, and in the deeper parts of the halo, there's a infalling part which is very new and dynamical, and it is not phase mixed with the rest of the halo, but it's there inside that boundary. And then there is just very recent mergers that are happening. So we've been also studying some, I won't go into the details of this, using machine learning to study, to look at these structures inside of dark matter halos, trying to see, are there natural boundaries? So one of the studies that had been working on with one of my master's students here at IISER is to just take a dark matter halo particle simulation and just ask, are there any natural dynamical boundaries that come out if you do something as simple as an unsupervised learning of its entire phase space, right? So what are the different structures inside dynamical structures inside dark matter halos? And we found some very surprising results that actually the largest cluster, so this is a typical simulation halo, and we're looking at it in this projected we do a higher dimensional clustering in a 60 phase space and find dynamical clusters and project them onto a 2D space. And we see that actually most of the particles inside the dark matter halo do form one dynamical cluster, but it does not actually contain all of the thing that we think is inside the virial radius of the halo. Actually, the older part of the halo actually separates out very neatly from the younger part of the halo. So so there is a lot of internal structure. I won't go into the details of that. Of course, the main point I want to get across is that these are dynamical complex objects, and they help us disentangle, observing them would help us disentangle questions about evolution and the nature. Okay, so then the question that Tarun was asking is, so what does so this is all in the space of simulation, but what does the real universe tell us about the structure of dark matter halos? Can we actually study them? Okay, so observing dark matter halos, I'll start off, and maybe I will probably mostly get time to talk about clusters. I've been involved in mostly understanding the dark matter distribution in massive galaxy clusters. These are sort of these are the largest gravitationally bound objects, and they actually give us a large dynamical range over which we can observe the halo. So we can really look at the dark matter halo from deep inside the scale radius to out to its virial radius with a lot of resolution. Okay, so so we can really study properties of dark matter halos in these objects, and there are things that shine in various different bands essentially, and various different parts of the electromagnetic spectrum. So we can really study different components that make up the dark matter halo. So I've mostly been involved with the DES group in observations of galaxy clusters, and the primary way in which we observe the dark matter distribution inside of these galaxy clusters is either we find a cluster in the sky and we look at the distribution of galaxies inside them. Okay, so think of these galaxies as subhalos. So they are the ones that live inside the substructures of these more massive halos that we've been talking about. So they also just trace the potential well. So we can study the distribution of galaxies to study the distribution of mass inside the underlying dark matter halo indirectly. And then we can also study the total mass and its distribution directly through the weak lensing of background galaxies. So if we have a large cluster in the field of background galaxies, we know that it'll distort the shapes of background galaxies. And we can measure this distortion, this correlated distortion, to study basically how the mass is distributed. Right. I can't see. Yeah, okay. Right. So we basically either do a projected galaxy number density, which is shown over here. So we do this because in the sky, particularly when we're working with a DS-like survey, we have photometry, and we are basically looking at everything in projection. So we measure the projected number galaxy densities, or we measure the lensing excess surface density, and we have an underlying model for the 3D density profile, which has all of these. So it has an inner ionosphere part, and it has an outer part, which has a sharp transition, right? So this sharp transition from the inner halo to the outer halo is exactly that phase space boundary. So this model incorporates incorporates that sharp transition to capture the effect of having a sharp halo boundary at the outskirts. So we basically forward model. We basically use this model to then constrain to then fit to these galaxy number densities and the excess surface density to get the underlying halo distribution. Right. So what I've primarily been working on in this regard is we've been looking at galaxy clusters that were selected using the Sunyaev-Zeldovich effect. So these are clusters that were identified. First, we worked with the SPT survey, and then we worked with the more updated catalogs from the ACT survey. So we essentially are looking at galaxy clusters from the ACT survey and looking at the distribution of galaxies from the DES survey around these ACT clusters. So you can ask me later, we also worked with optical clusters, but these SZ clusters are thought to be less prone to systematics. So we are using these, we have a sample of about 1200 SZ clusters in the footprint of DES, which we are using to then study the galaxy distribution around these SZ clusters or the weak lensing of around these clusters. For the most recent studies that we've done, we have about 1200 clusters with SNR greater than 4 between a redshift of about 0.2 to 0.7. And these are primarily massive clusters that have masses greater than 10 to the 14. Here's the mass distribution and the SNR of these objects. Right. So we use these clusters, go ahead and measure the lensing and the galaxy distribution. So this is actually data. So this is the measured distribution of galaxies. So on the left-hand panel, it is the projected number density of galaxies as a function of radius for these ACT clusters. So these are the distribution of DES galaxies around ACT clusters. So the black shaded region is the model. So the black curve essentially is the distribution of all galaxies above some magnitude limit. So all galaxies that are sort of brighter than 0.1 L starish around these ACT clusters, and the different colors corresponds to galaxies of different star formation, or red, blue, and green galaxies around these objects. So the left panel is the density, just the raw measurement, and the model fits shown in gray. On the right panel is the inferred slope that we get by fitting our demografts of our 3D density model to it. So as you can see, so this is the logarithmic slope as a function of radius. And as you can see that the feature that I was talking about is this sharp steepening of the density profile near the outskirts is very clearly evident in almost all of the components. So all the galaxies is this black shaded region. The red galaxies show a very deep feature. So the distribution of red galaxies around clusters shows a very deep feature, whereas blue and green galaxies around these objects show fainter features. We'll come back to that. So other than just measuring the galaxy distribution, we also measure weak lensing. So the weak lensing profile. So again, on the bottom panel is the distance from the center of the SZ cluster. So these are stacks also. So these are not individual clusters. These are stacked measurements of the profile.
So Susmita, just to interrupt the previous slide, there's a trend from red, green to blue. of the, whatever the splashback radius, I guess, the dashed line is the splashback radius.
The dashed line is, yes, for the black curve. Yeah.
Yeah, but what I'm saying is that seems to have a trend with the color of the galaxies.
That's correct.
Is that understood?
Yeah, I'll come to that.
Okay.
Yes, that is understood. So that is, yes. So yeah, so that we can, because unlike particles, galaxies are evolving in the dark matter halo. So that has some very important implications for where this minimum of the slope of the galaxy will occur inside a halo. And it's actually a probe of how long objects have been inside. So I'll come to
Just
that.
remind me, red, green, and blue sort of refer to the age of the thing or galaxies,
Yes,
right?
so
I mean, in some sense.
yes, so red galaxies are typically galaxies that are elliptical, have very low star formation rates. Blue galaxies are star-forming disk-like galaxies. Okay, so that's a good question. So are you asking whether they're older galaxies, younger galaxies?
Yeah. Is there a, known?
Yeah, it's not a very clear. Uh, so it's true that the red galaxies have formed most of their stars early, whereas the blue galaxies are still forming stars. So whether this is right, so there is this effect that near clusters you tend to see redder galaxies than in the field. So some people think that this might just be because redder galaxies are somehow older than bluer galaxies. And cluster fields are older fields. But essentially, so that's called the age. What I'm forgetting the term. Anyway, so that's one way of explaining why there are more red galaxies near cluster fields. But the other way of explaining is that people think is that there might, because when objects fall into clusters, they get quenched. So the star forming gas gets stripped off from the galaxies because of the cluster's hot environment. So there are these two different ways of understanding why there are red and blue galaxies. So yeah, this actually is, so there's probably both of this. So this work actually shows this is actually more showing the effect of the quenching, as we have found out, essentially.
So I just wanted to tell you that, I recall that Bishwit Pandey, and when he was a postdoc, I think there was a work I was involved in where we showed, infall through filaments into galaxies and into clusters.
Yeah.
And if I remember right, either that paper or the papers we read during that time, I'm very unclear here. I mean, had a, kind of as if there was a procession of red, green,
Yes.
and blue along, from the cluster center going out or something.
Absolutely. Yes.
Yeah. So that I thought my impression was that has to do with the age, but if that's interesting that there's a alternate possibility.
Yes.
Okay.
Yeah, it would be interesting to, I don't know if you were doing this with observations or with
No observation.
Okay, these are
those
observations.
hydrocodes. I mean, I absolutely don't recall it. You have to,
okay.
pick up
Yeah,
the
because it would
paper
be
and.
interesting to test these two different, like how do we test these two different models?
Yeah. So, yeah, I will look up the paper. You might do it faster than Pandey and me.
Sure.
And then there were probably someone else also, but
okay. Yeah.
Vishwet
Sure.
Pandey.
I'll take it. Yeah. So right. So so I'll come back to that in a second. So the other thing that when we were looking at the lensing of galaxies, so we also look at so here I'm plotting delta sigma, which is essentially the lensing observable, gamma t times sigma critical. Gamma t is the shear of the galaxies due to lensing. So I'm plotting r times delta sigma, and the data points are from TS lensing measurements. And right, and the right hand panel again is the fitted slope from our model fitting to this lensing distribution around the galaxy clusters. And you again, lensing of course is a much harder measurement with larger error bars, so we do see an evidence for a steepening, but of course it's less significant than that we see in the galaxies themselves. So one of the nice things actually in this study that we wanted to point out, so here we are essentially tracing the halo in two different ways. One is through this directly through the mass, and one is through the galaxies. And one of the things which is actually not quite obvious, it might seem obvious here, is that what we found is that the galaxies and the dark matter actually tend to follow each other quite well, right? So people, think of different scale dependent biases for galaxies and how that would change as a function of radius, but the shape of the galaxy distribution around the clusters and the shape of the mass distribution of the clusters, which is shown in this red shaded region and the galaxies in the blue shaded region, is actually quite well, agree with each other quite well. Down to very small scales. If you looked at low mass galaxies around these clusters, you would start to see some shallowing over here. So the slope would become shallower because of tidal effects. But overall, they essentially follow each other quite closely. Right. So that was, and the splashback radius for the galaxies and lensing also agree with each other fairly well. So that was, so this is actually also not the case in simulations. In simulations, because of very large resolution effects, the inner regions of galaxies look very different from the dark matter because you just destroy them in many different ways. Right. So this was the overall profile. Of course, as Tarun was asking, what is going on with these galaxies of different colors? Actually, galaxies, coincidentally, give us a way of testing or the closer, the more closely the phase space structure of halos, because dark matter particles actually don't change as they move around inside the halo through the tracing the phase space, essentially, right, orbiting. But galaxies, as they orbit, they may change, particularly because a cluster is a very hot environment. And when a galaxy falls into a cluster, the cold gas might be Ram pressure stripped or get heated up and not collapse into stars. So it is expected that so this is called star formation quenching inside of galaxy clusters. So essentially, if this process is happening, so this is seen in hydro simulations and so on, but if this process is actually happening in nature, you should, and if these are happening over the timescales of orbital timescales inside of cluster, you should see their effect in these distributions. So for example, as I was saying, you might have a red galaxy, sorry, you might have a blue galaxy that falls in. So this is, the gray part is a halo. So if you have a blue galaxy that is falling into a dark matter cluster, so this is a simple toy picture of the idea. As it moves through the cluster, if its star formation is quenching, it essentially, the blue, the overall blue color will eventually turn red and non-star forming. So as it traverses to the halo, a galaxy might change, right? Now, so this is the phase space. So a typical dark matter particle or galaxy will trace this path. So it'll come in and then start orbiting, and over time its orbits will shrink. So if you take, if a galaxy comes in, if a blue galaxy comes in, and by the time it reaches pericenter, that is the least distance from the center of the halo, if it quenches all of its star formation, it'll never actually reach the boundary. So it'll never actually reach splashback, right? Before it reaches splashback, the galaxy will have turned red, right? If it turns red somewhere in its first orbit, it'll stop its transition from multi-stream. So look at the blue stream. It stays blue, and then by the time it reaches this point in its orbit, it's become mostly non-star forming, and its phase space structure will show a crossover from two streams, so one infall stream and one orbiting stream, to a single stream, just the infall stream, at a smaller radius, right? So essentially, this is what is happening. If you take particles that have entered the halos at different time, and you see what part of the phase space they stretch out, you will start to see that their density slopes, the minimum of the slope actually changes as a function of how long they've been inside the cluster. Right. So this is a model that turns out, explains the observations fairly well. So so this can then say that, okay, most of the galaxies that have reached splashback are actually red. So you see a very deep splashback feature in red, whereas the blue galaxies are not really showing splashback. They have not really reached splashback. They are showing a phase space jump at a much smaller radius, or the green galaxies are showing a phase space jump at a much smaller radius, right? So, right. So we use this to if this were given this model, we try to constrain how long have these galaxies actually been inside these clusters, and the ages of these galaxies inside of these clusters. And we also put some basic constraints on the quenching time scale inside of these objects. So with these galaxies, we can now probe, and with this picture, we can now ask more nuanced questions of the galaxy distributions inside these objects, and understanding the halo then really helps us sort of even to understand galaxy evolution inside of these objects. Right. So that was galaxy evolution. So now that given these measurements, given that DES and going ahead with LSST, and also because our SZ samples are actually, we haven't worked with the most recent SZ ACT sample, will hopefully become larger. We will really start to get very precise measurements even in weak lensing. Right. So one of the things that we wanted to ask, because weak lensing directly measures the dark matter mass, the dark matter profile, we wanted to ask, or it can be connected in a more direct way. You can also do it with galaxies, but we wanted to ask if whatever we are observing about the halo profiles, are they consistent with cold dark matter? Right. So we have, theoretically, through simulations we've really studied cold dark matter quite well. So we went and looked at these slope profiles, which is the pink shaded region over here, dark pink shaded region, and compared it with expectations from simulations, which are these black dashed lines. And NFW is this green dashed line over here. So as expected, it's not consistent with NFW. I mean, it is consistent actually. The NFW here does not. So eventually the profile is expected to go back to background, which is why it falls and then goes up. So NFW will also at some point actually go up, but it's basically steeper than -3 in the outskirts. But what we saw, one of the things that we saw is that the inner profile is consistently steeper than what we expect from CDM simulation. So these are not models. These are directly, we take n-body simulations of halos and stack them and find their slope as a function of radius, mass matching the two samples. And we find that these are consistently steeper. The observed profiles have slopes that are -2, whereas the n-body simulations slopes are shallower. Of course, this is, initial measurements, and these are not very significant right now, even though many points are actually steeper than that, but we expect to, make these measurements much better in the future. So one of the things that we've been studying is, we went ahead and asked, okay, are these profiles? Then we've been studying dark matter models, particularly the inner profiles, even more than the outer profiles, are sensitive to models of dark matter. One of the things that we had pointed out is that while you expect clusters and galaxies to core, if you have self-interacting dark matter, not only do you get a core, you actually push matter out. So this is a CDM profile, and if you have self-interacting dark matter, you tend to form this, the inner profile does not remain cuspy, it becomes cored inside. And you form a core, but you also push matter to the outskirts. Okay, it's a simple mass conservation process. So you actually tend to become steeper than CDM in the outer regions of the halos. Now, measuring the core is, of course, the largest signal is here, but it's also more complicated because there's a huge, massive galaxy over there. But lensing measurements actually are getting so precise that we can also start to measure these small differences in the outer profiles of galaxy clusters or groups. Actually, even in future, we want to do it with smaller galaxies as well. So if you look at the lensing prediction as a function of radius for different models of SI, self-interacting dark matter, for different cross-sections of self-interacting dark matter over here, you see that there's an excess density before it. So there's an excess density in this part. Black is CDM, the red, blue is excess. And in the inner region, again, so this is lensing, so it looks a little different from the 3D density profile. And then you see a turnover, which actually starts to correspond to the core again. So these are different, these are predictions that we had made some time back, forecasts for LSST and DES year 5. And more recently, that you should start measuring these, you should be able to start constraining these cross sections just from weak lensing. And more recently, we actually went ahead and looked at those constraints. So these are the measurements that I was showing you from lensing and CDM, and these are the different models of dark matter, which we have run simulations for. And you can start to go and ask, so this is the steepening region. In fact, what we are seeing is we are actually starting to see effects of the core even in the regions that we are observing over here. So we can go ahead. So as you can see that the CDM is actually, that the measurements are actually, the delta sigma measure is slightly higher than what you expect in CDM as well. So we go and ask what kind of models are these consistent with. Not only did we do this with self-interacting elastic scattering models, with Yiming and others, we've also been looking at dissipative dark matter models. So an interesting thing happens. Actually, this happens even in elastic scattering. So while you expect a core, while the first part of the gravithermal evolution gives you a core in the center, at some point, the direction, if you have self-interactions, at some point you actually expect, if your interactions become too frequent compared to the dynamical timescale on that, at that radius, you actually enter a phase of core collapse. So you collapse. Instead of forming a core, you start to collapse to a very steep cusp in the inner ring. You can actually become even steeper than NFW. So we've also been, and this can happen even faster if you have dissipative dark matter models. That is, dark matter particles there are essentially, two states of dark matter particles. So the dark matter particles can decay into sort of a chi dash state, and then can scatter into a chi dash state, and that chi dash state then can decay, emitting a photon that escapes from the halo. So you actually lose energy. So if you lose energy, you actually end up collapsing even faster. Not going into the details of the model, so we also try to put in, so we can predict what the profiles of halos will look if we have dissipative dark matter. So the blue dashed lines over here are, if you have dissipative dark matter, you will actually start to become even steeper than NFW, and you can then use these measurements to put constraints on what kind of dissipations are available. So in this work, we went ahead and we looked not only for constraints on elastic scattering. So these are the first of its kind constraints for dark matter self-interactions from weak lensing in clusters. They are, what we found is that they are consistent with the bullet cluster constraints of, the bullet cluster constraint is about 2 centimeters square per gram. So we are 1 to 2 centimeters square per gram. So we are consistent. So at 99%, we are consistent with bullet cluster. And then we put some novel constraints on the scattering of inelastic or dissipative dark matter scattering as well. Right. So these are in some senses, this is DES year 3 result across ACT clusters. But going ahead, we've actually not yet done the Y5 analysis or year 6 analysis. And with LSST, these are expected to get, I have these constraint plots. Right. So with LSST, we are really expected to get, so these are basically how our current, the blue dash line is our current constraining capacity. With something like LSST, we'll essentially get to these, like these deepest, these solid blue lines. So we are going to do much better in the future, and not just, so because these effects are there in the outer profiles, which is away from the core, away from the baryonic effects of having a massive galaxy over there, we can also just simply use the outer profile to get really, really strong constraints. So we can just use this part to get really strong constraints on the dark matter cross sections, just simply using weak lensing of galaxy clusters. Right. So these are only galaxy clusters. We can also just go ahead and do this with groups and galaxies. So we are working on that. It's even more interesting in the group regime, because there the cross sections are allowed to be higher. So it will be really interesting to see what kind of constraints we can put weak lensing over there. Right. So I'm reaching the end of the hour. Right. So I just wanted to say that along with measuring the dark matter, and through galaxies or through lensing. There's also been some very interesting work by some of my collaborators, in particular being led by Dhaya and Bajaganai, who are measuring the gas distribution inside of these clusters out to through stacked thermal SZ, and trying to see if this flashback-like feature is also seen in the gas distribution. This paper is a little bit from some time back now, but essentially, as of now, we find that there is, just like the dark matter, you expect the gas to have a virial shock at its boundary. So that also creates a very sharp feature. And there has been some very interesting conversation in the literature whether you expect this shock boundary to coincide with the dark matter boundary, or whether the shock boundary can extend much further out. So there's been some very interesting work by Dhaya, who's been looking at this. And he's currently found things that are consistent with splashback, but there might be other features in the. So this is really the gas at the outskirts of the halo and its properties. So it gets noisier as we go outside, but we're hoping to learn much more about this as well in future surveys. Right, and then I won't have I think a lot of time to talk about this. So galaxy clusters we are studying to it's very promising, because these are really well-resolved massive objects in the sky where we can really look very carefully at many different scales. But our surveys are getting really, really promising. And one of the studies that I've been very excited about is looking at the faint galaxy regime. And actually, the faint galaxy regime is extremely exciting for dark matter because the baryonic effects are much lower when you go to faint galaxies, right? That's why a lot of our forecast problem and everything have come from our intuition of dwarf galaxies, because we expect these to be dark matter dominated objects. Right. So one of now we are using DES. So our usually a sample of dwarf galaxies was our Milky Way dwarfs and in the local universe. But now with these larger surveys, we can also actually get large statistical samples of dwarf galaxies. And we've been working with some techniques to actually identify faint galaxies that are close to us, rather than bright galaxies that are really, really far away from us. So we've been working with Alex Amon, Risa Wexler, and their students who have developed this machine learning algorithm to identify faint galaxies that are close to us. And we use this method in DES to also estimate the redshift of these galaxies, and then go ahead and measure the weak lensing profiles around them. And so in some work now in about last-ish year, we actually went and measured the delta sigma around faint galaxies, and these galaxies have stellar masses as low as 10 to the 8, 10 to the 10, so to 10 to the 10. So these are the highest mass bin is stellar mass of 10 to the 10, lowest mass bin is 10 to the 8. So they are kind of entering into the LMC like regime. And we actually start to see the measurements, we start to trace the one halo, internal halo structure already with these measurements. And so this is the lowest mass bin, this is the highest mass bin, and then you can go and compare with NFW, and we have, I think this is some of the first measurements at this mass scale where we resolve the inner one halo term. Right. So so this is typically where you expect the virial radius to be. So you're seeing several points inside of the virial radius. So several points telling us about the distribution of galaxies. So they agree, as of now, given the error bars, they are very, very consistent with CDM simulations. But again, the story will hopefully get more interesting as we get better measurements. Right. So yeah, and then we can use them to ask much more nuanced questions about the nature of dark matter and so on. Right. So I will stop here and put up my summary slide. I think I wanted to give an overview of all the different things that we can, given our current observations, where we are today, it's a really exciting time to study the internal structures of dark matter halos in a lot of detail. And there is a lot of information over there, and which we can utilize to understand, um, ask very detailed questions about the nature of dark matter and gravity. There's a lot to do. I think in future, I'm very excited about also doing this in redshift space and also pushing to low dark matter mass scales. And yeah, so with that, I'll stop here, and I'll take any questions. Yeah, I've put CMB S4 over here, but of course, I just learned today that that has probably lost funding. So yeah, but we have various things to do. Okay, thank you. And
thank you for giving very detailed and exciting talk on dark matter halo measurements. Audience can ask question if you can raise hand or you can unmute. Yeah, Tarun.
Right. So this is something that about the, I mean, Sayan Saha, my former student,
yeah,
was working on improving the mass estimates from lensing of clusters and CMB polarization,
yeah,
and they
yeah.
have now, if I recall right, the whole thing was based on the NFW profile.
Yes,
So
yes.
what's your comment on the appropriateness of doing that, given whatever you told us about the mass? There's there's
Yes,
stuff outside, right? That
yes, yes,
and
yes.
so do
Yeah,
you think
when
that?
Shayan was here, we discussed this quite a bit. It would be really interesting. So I should say that given the Edabas, the mass estimates from NFW also do quite well. So
Hmm.
that will already be there. But it is correct that the true underlying model is not NF. It will not be NFW, especially for these clusters. You will see a very steep cutoff at the edges. So we had discussed with Shayan to actually use a Dima-Kravtsov like model to try to incorporate it in the mass estimate. So there's been some work that also shows how the mass within splashback is actually gives you a more universal mass function, for example. And particularly while you're, a lot of these cluster studies are based on measuring that mass function really, really well. So to get cosmology. So yeah, it will have implications for that. So we had discussed with Shayan. I think it got lost over the many years, but it's
Okay.
something.
Oh, okay. No, but no, it might be useful to prod him to look at. I mean, I thought that was an obvious problem because, you're putting in a particular profile, deriving mass estimates, and then, that's the only observation we have of the mass profile if you wanted to use it, right? I mean,
Correct. Yes, yes, yes. But now,
okay.
it's pretty easy to extend it to use a different mass profile.
Yeah.
Yeah. People have sort of been aware that our mass profiles don't work somehow in the transition region. There are all of these halo exclusion effects and stuff. So I think now that literature is getting much more clarity. Yeah. So I think it's a very obvious extension. Yeah.
Thanks.
Okay, anyone? I have a couple of questions. So this FR gravity, modified gravity plot you showed, so it looks very
Yeah.
similar to the standard one, no? Or you can distinguish it.
Okay. Yeah. You mean it? You couldn't see the difference by eye? Is that what you're saying?
By eye, at least.
Okay. So maybe I should point out what it is because I just flashed it, didn't go into. Okay. So the effect is a little bit. Can you see?
Yes.
Okay. Yeah. So this is GR, right? So what happens is, notice the x-axis, right? So for the lowest mass galaxies in GR, you have the black curve. So this is galaxies around massive clusters and their distribution, right? So what happens is as you change the mass of the galaxy that you're looking at, the splashback radius is expected to move inside
Okay.
because of dynamical friction. That dynamical friction becomes much slower if you have, so this movement between the black and the green, which you can see is still beyond 1 over here, becomes, it's a small effect, but it becomes the movement becomes much slower in F of R gravity because these objects are falling in from a region of sort of 4/3 G, to a region of g, right, in these modified gravity models. So they come in with very high velocity, so they feel much lesser dynamical friction. So you get effects of order actually a 5-ish%. This is in log scale, 5 to 10-ish% in the movement of the splashback as you change the galaxy mass, which is something that we can actually do quite well. Yeah. So it'll be a 10-ish% effect, and we can, in the galaxy distribution, we can measure it definitely to that level. So we haven't actually done the measurements yet, the actual constraints yet, but it should be observable. Yeah.
Okay.
Yeah. So it's basically just how it moves becomes different. Yeah.
Okay.
Yeah.
And can you explain a bit about this self-interacting dark matter thing?
Yeah. What did you, sorry, what were you saying?
Can you explain a bit about this self-interacting dark matter, like what kind of interaction it has?
Yeah, so these are basically, so there are two various models. So this is the simple vanilla hard sphere scattering. So people look at various models. So one is just the simple elastic scattering model, which is isotropic. Then we also look at, but these are all elastic. Then we also look at velocity dependent elastic models. So there's a Rutherford-like fall off at higher velocities, and the inner velocities are isotropic and flat. So we've currently we think that there should be, from observations, I think it's believed that there should be some velocity dependence in the interactions. So essentially, we look in basically in these two regimes. Is that what you're asking, or some more?
Yeah.
Yeah.
And this stack profile of Y that you showed towards the end. So there's a difference between ACT and SPT at high distance. So probably it is within the error bars, but like how reliable is the measurement at?
Yeah, I think the mass distribution of the SPT and ACT might be slightly different.
Okay. So that's why there is a difference.
Yes. But you're right, there is some difference. So the mass and redshift distributions can be slightly different between the two. Yeah.
And the theory is basically the profile, density profile that you use.
Yeah, the theory is the density profile. These are from simulations. Turns out to be, we don't know why it's actually steeper than the hydro simulations. We spent quite a bit of time trying to understand this. I think the simulations don't model the electrons plasma, which is what we are observing in SZ. So there's some difference between that and what we're seeing. Yeah, we were a little confused as to why the simulations don't show a similar steepening. Yeah, so it's actually an observational effect that we're seeing. Yeah.
And this from the simulation, this density profile can be written with some analytical function.
Yeah, I think people do write the density profile from some simple hydrostatic equilibrium assumptions. Yeah, these are from simulation. This is not the analytic one. Yeah.
Okay. Yeah. Anybody else? There is a question in the chat. Is CMB S4 affected by funding? What would be the relationship of modified GR gravity and the CDM model? How can we approach? So it's like beginner questions.
Yeah. I think this I just heard that CMBS4 funding has been cancelled this morning. And is that a separate question? What would be the relationship in the CDM model? This is with respect to so I think so what we looked at was a few specific modified gravity models. I think to actually put constraints on this, we will so one challenge with modified gravity models is that they're very difficult to simulate. They're much more time consuming and so on. So to get a full constraint, we would have to run it on various parts of the parameter space. So that is something that we want to look into. And also, I think now there are even stronger constraints. So the models of FFR that we had worked on, I think have been now probably have been even ruled out. So we haven't done this fully. But I'm not sure I completely understand your question. It would be great if you can explain. Otherwise, Right. I mean, in principle, you can do CDM plus modified gravity, or you can also do SIDM and modified gravity and all combinations and see what you get. Yeah. Yeah. Welcome.
No more question. Let's thank the speaker once again. Okay, thank you for giving a very nice talk, and thank you all for attending it. Yeah.
Thanks, Susmita.
Thanks. Nice to see you all.
Yeah.
Yeah. Bye.
Bye.
Bye.